this, so this is the other point that I'm trying to make. When this definition itself, just this sentence is beautiful. So I'm going back to what a sequence is. So we've gone over this before. So the definition of a sequence is a function whose domain is, how many people find this extremely powerfully exciting sentence? Gavin says yes, Ryan says yes, we have another. It's really super cool. It's so concise and so precise. And you have to know what a function is, what a domain is, what natural numbers are in order to unpack it. So in other words, it is saying we can take sequence is, thing is dying. Sequence is a function. So, and this is the maps to notation of a function. So sequence is a function f that goes, whose domain is n. So the input into the function comes from the natural numbers. So natural numbers are mapped into or mapped to real numbers. And then everybody knows what natural numbers are, 1, 2, 3, 4, 5. So if I wrote, so here is the example of when we look at sequences, they show up as sequences of a sub 1, a sub 2, a sub 3, all the way to an, all the way forever. So the key thing is that we're always thinking about this as an infinite sequence. Otherwise, it's not fun. So this thing here, which thing here is the domain? Or even this one. There are two things here, right? We have an A and a subscript. Is A the domain, or is it the subscript which is the domain? Deep thoughts. Very good. So subscript, it takes 1, and then what is the output? So in other words, here we're going to have 1, 2, 3. These are the subscripts. Okay, 3, comma, dot, or dot forever. And subscript is called, it's the index. Oh, Jake is here. Very good. I was just bitching about you. Like, where is Jake? Yeah, like you blinked out. I said that, which is pretty hardcore insulting. And then R is the whole damn thing. What could R1 be? It could be anything, right? Let's say it's 3.2. 3.2 looks like a real number, so that's why I put that there. Okay, and again, so this is what we get here. So on this side, the input is 1. 1 gets us what? A1. What does 2 gets us? The second term of the sequence, which is A sub 2. Whatever its value is, right? We don't know. And then, I mean, we know. And then when we put 3 into this function, maybe the function was n squared, we're going to get here. If we put 3 here, we're going to get 9 here. If we put, right? No. If that was the formula, we don't have the formula. So ignore what I just said. And bam, 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 bam. Okay, so that is the definition of a function. And now let's move on to what we will actually be using in the exam. Okay, so let's go over that again. Before I do that, let's look at a sequence quickly, just randomly. So people, give me a first term of a sequence of real numbers. So I'm going to do 1, 2, 2, just to make it look like a real number. All right, so we have 1.22 and an angry look to Mr. Jake. How's your arm? Okay, next, give me another number. Seven, okay, 7.34. Okay, next. $120 million. Mr. T's inheritance. Okay, please. All right, next. Oh, cool, 139 million. And it goes on forever. So this term is A1. This is A2. So somebody says, hey, what is the A4? It's this guy here. A3. And again, for the non-science majors, how do we real number line? Let's put 0 here. 1.22 is going to be right here. So this is our A1. 7 is here. 7.34 right here. So this is 7. This was 1. Our A2 is sitting here. Our A3 is our A4 is right here maybe. Is this, so what I'm trying to do is how we take a sequence and stick it on the number line. Okay? All right, so that's what had happened after. Now, excuse me. That's my original language. When I go home, we speak like, and then my brothers and sisters go, that means dinner is at 8. Thank you. Okay. Okay, all right. So is this whole idea of a sequence clear now? Now, what's happening here is these sequences seems to not have a limit. They seem to be going forever to the right. Though, okay, which means that the sequences that go to the right do not have a limit. Again, they also have the same problem. They do not have, so they're going towards the negative numbers, and they also do not have a limit. And they can also go on forever. So you can have a sequence of, you could go from the positive numbers towards the negative forever to the left side. Very good question. So, but we usually look at the positive side, but you can have both. Actually, there are both of them. So now let's look at the definition of a convergent sequence. And what I'm going to do is not go over the definition because we already did that. I'm going to draw the diagram and some other things. So here is a real number line. And so I'll give you all the notation. And then what's happening? We have our A1 here, A2 here, A3, and then okay, and then I have I've decided that this is where my this A without a subscript, what is that? Is it in the sequence? Not necessarily. That's why I remember that picture. So that, and because it doesn't have a subscript, it's also saying maybe it isn't an element of the sequence. Okay. Remember that picture where L was 5 and then I did the dot, dot, dot. I don't know if you were there, Chris. So that's something I always used to ask you guys, like, is it not necessary? Limit doesn't have to be a value of the function. If it is, then the function is continuous, right? So same thing here. This can be element of the sequence and it doesn't have to be. All right, so what that means is that if I, and so what am I doing here? Anybody? What happens to the sequence once it enters this interval here? Sorry. Not oscillate, but stay within epsilon distance of the limit here. This is our limit. It does kind of oscillate, but that actually means that if you have a sequence that goes to 1, 0, 1, 0, 1, 0, it never actually, if your sequence only has 1, 0, 1, 0, 1, 0, it doesn't have a limit. It's oscillating. So this is different. Okay, so here we go. And I show that right here, right? All right. What is missing from this picture here? We need a specific term after which all the terms end up inside this open interval, a minus epsilon and a plus epsilon. So that term, its index is, you can look at the exam one that I just sent you and somebody can tell me, we need another term. It's not this, it's the next term, maybe next term, the fourth term. So I'm going to say now that after the fourth term in this sequence, every term after the fourth term ends up only within epsilon distance, and that never changes. So what is the subscript for the fourth term, after which we're going to use what letter? An uppercase? Folks, this is the most exciting moment of the lecture today. This giant N. Remember the N? And the definition goes that, what is the definition? All the indices, all the terms after the term with the uppercase N will be within epsilon distance of the limit A. Okay? So in other words, after this, all the ANs will be within epsilon distance. If I put equal to sign, this term after which all the terms are within epsilon distance can be represented inside here. If I take this out, then the nth term has to be outside. Okay, so it can be either, if I do this, this means it's either inside this open interval, this neighborhood, or so if I have this, so either the A sub uppercase N is inside this neighborhood, or right before it, okay, right here, or if you just have this. So it depends on the book that you're doing. Okay, now everybody knows what N is. I'm going to put N back here. So here we go. After this AN term, no other term of the sequence it's not gonna show up here. There will be no terms here, right? Only within this thing here and this thing. So N depends on what? There's a number, a symbol in here that N's value depends. N is not written on the stone. It's just the term after which it better be within this. What if this thing was what if I move this thing to, so I'm going to do that. Excuse me. Epsilon, let's say we started out epsilon as 1, length of 1, right? 1 on this side, a plus 1, a minus 1. What if I made epsilon half? So now I'm saying epsilon is here, right? And okay, now if you look at the picture, epsilon has shrunk. Is this an anymore? No, because after an, there's another term of the sequence, another term of a sequence, another term of the sequence, and then all the rest of the terms to infinity are within epsilon distance of the limit a. Therefore, this term is not going to work as a threshold term, as I call it. There's no actual term name for it. So we need to move. We need to find another n. If this n was equal to 4, we have to go with 5, 6, 7th. It's the 7th term, after which every term will be inside. All right, so it depends on, there's nothing special about that term. It just depends on how big your epsilon you chose. And the fact is that if you make this epsilon too big, it can become ridiculous, but it should always work. I could make it still smaller. We'll just have to choose an uppercase n index a term further to the right. For that term, after which all the terms will be within epsilon distance. Does everybody? So what you're learning right now is the nature of epsilon. Epsilon can be any size. And in this case, it determines the uppercase n. An index number like we had 4 first, we made epsilon smaller. So then we had to increase, then we had to go with the number 7 as our uppercase n. Any questions or confusions? No? Okay. So here I'm saying, here is where all the ANs are, right? And they never leave this neighborhood. What's another way to express that all? I'm going to start here. I'm going to say that here's our expression, epsilon distance. So I keep saying this, right? All terms an, all terms an are within epsilon distance of the limit a. Everybody wrote that down. Now let's do some math notation. How do we do that? We are saying that all terms an, if you take each and every an, as in you choose any one of these one by one, the infinite number of these terms in there. What's the first term after a sub uppercase n inside this interval? What's the index number of that? N, a billion. Very good. N1 or 8, right? And then what's the next term? N2, N3, N4, and so on. Very good. All right. So I pick every an, every time I pick an an, a term from inside that interval, that neighborhood, and I subtract it from a, their distance is within epsilon. How do I say that? Is this distance or is it just subtraction? This is just difference, right? How do we make a difference and call it a distance? The distance is always positive. Yes, exactly. Very good. Emma is telling us we need the bars. Why do we need the bars? Because this subtraction would be negative, right? If I took an AN from this side, from the right-hand side, and subtracted it from here, I will get a, no, if I did the other way around. If I took an AN from here, which would be smaller, and then A would be bigger, and I'll get a negative number. Every time I pick an AN from the left-hand side of the limit A, I'm going to get a negative number. That is not a distance, because our whole idea is that everything is within epsilon distance. In order to make this difference always positive, and if I took an AN from here, subtracted from A, since A is a smaller number, it's to the left of any term here, it will always be positive. But for these numbers, this thing doesn't work, because AN is smaller than A. If AN is smaller than A, if you subtract these two numbers, you will get a negative number. Okay, who's confused about this? Raise your hand. How do you make this difference into a distance, as Emma pointed out? Now what we're talking about is positive always. When you get a negative number, you apply the absolute value sign, it becomes positive. If it's already positive, you don't do anything. Okay. And now this distance is positive because distances are always positive. Unless you're trying to get back to Denver, then that's a very negative situation on Alrighty then, here we go. What should I put here, folks? Yes, excellent. So we got the absolute value signs here. And what is this saying? All terms AN are always within epsilon, which is a positive number of A. All the distances from all the distances of each of the AN term, these terms that are clustering terms is the term I used before, are always within epsilon distance of that. Okay, and epsilon can be what? We started out with epsilon being 1, then we made it smaller, we went to 1.5, right? Make it smaller. And if we made it even smaller, we would have to find our n will become bigger, either inside or outside. Okay. This thing? Yeah, what this is saying is that all the ANs are clustering around A, and they're within epsilon distance of A. They will never be here. Any of the terms after the subscript uppercase n will always be within these, within right here, only here, never here, and never go back in that direction. Once they enter this neighborhood, they never leave, is what this is saying. That all the terms, these are, what's another way? Oh, this is, you could just do this. You take A here, and then all the ANs, these are the ANs, AN, are always within epsilon of A. They're never this point either. This is a point on the real number line, and these ANs never fall here. After the uppercase N, all the terms will always fall here. All these ANs will always fall around A, cluster around A within this distance. Which means that that's what's your question. Which means that if this is true, your sequence of terms, the terms of the sequence do not go on forever to the right, but they actually start to cluster around here, even though the terms are infinite. So there is a limit around which they cluster. They don't go on forever. So it is a convergent sequence. Very good. So that's, if you have, so in other words, if you have this situation, then the sequence that is made up out of these terms is a convergent sequence. If you don't have this situation, then it's not a convergent sequence. It is probably going on forever, or it's oscillating. Okay. Yes, you're good. Very good. All right. Now, yeah, I wouldn't have gone there, which is where I should have gone right after that. And then again, look at the definition in the exam one. I copy pasted it from the PowerPoint onto there. Now is, okay. So now is the time to do the poem. I think we're done with this, right? Yes. Okay. Let's do the poem. Okay. So I'm going to write the poem. Oh, no, we're not done with this. Sorry. There's one other thing. Before we get to the poem, what are the elements of this definition? So if we have a convergence sequence, if we have, what are the list of things we need? So from the definition, we need to have this happening, right? What else? There's another thing. There needs to exist an index number for a term after which all the terms are always within epsilon distance of the limit. So did somebody say why, or was that from outside? Shit. So there needs to exist what? What else do we need? The condition that we need is n. First of all, there needs to exist an n, a natural number n, and n is shit. Let me write this again. This is just a letter n, not natural number symbol. Okay, what else do we need? Anybody? No? I think that's it, right? If this condition is true and this condition is true, this can only be true if there is an n, and this n here is the index number for all index numbers for all the terms after the term that has the uppercase n index number, then they will exist here. So the order is reversed. I'll just do that. Okay. All right. So does anybody have the poem? I'm going to write the poem down here. It's for the exam. So I'm going to write, and then somebody's going to help me. Fame is a BITCH. Fame is a B. It has a song, or is a song? It has a song. It has a sting. It has a song. And then after the song, is there a dash? All right. So we got, it has a song. It has a sting. Aha. Aha. It has, aha. AH, comma. And then this is lowercase. It has a wing. Shit, it too has a, oh yeah. Okay, thank God. Very good. All right, thank you, Miss Sophia. I'm saying fame is a B. Is what kind of line is that? Somebody says, hey, define, tell me. Yeah, what were you saying, Zara? Tell me what fame is. And you're gonna say, fame is a B. Yeah, B. So, all right. And you go, really? Fame is a B? Really? What are the other conditions that come along, right? It has a song and it has a sting. What are the conditions for this to be convergent? This, right? This has to be true, this has to be true, and then this will be true. So for fame to be a B, it better have, because B's have this, they have this, and they also have this. If these three conditions are true, then we're talking about a B, and that these conditions should also apply to fame itself directly. So what we're doing is what did she actually want to say? This is what she wanted to say. She wanted to say fame is a song, has a sting, and travels, or a wing. Travels, spreads. She just added this. This is kind of like this thing here. Yes. It says pause. Thank you. That is a wonderful moment because I've done this here. Yeah, okay. So then you can watch this thing. All right. So are we already, and I'm thinking maybe this definition isn't the best definition where there are conditions. What do you think, Ryan, right? We could have used some other definition which resembled this thing. Oh, no, or some other definition of some other mathematical structure. This will work, right? Okay. Oh, you're doing it like that. Okay. So and then you have that, right? Okay. Yeah. So we can add things to that. Very good. What he's saying is, since we don't have the definition, I'm going to add little bits from the definition. It's not just these two conditions. So let's do that. This will be this is going to be 2, this is going to be 3, and then there's another set of conditions, things that need to exist and which are, oh yeah, this doesn't do it. So that we need to have, there exists an epsilon. I forgot how to write an epsilon, which is a positive number. And what was the other thing? And then n has to exist. So we have that there. Oh yeah, there. No, yeah, sorry. So this is for all. So upside down, because right, that's what we were looking at. For all epsilons, it should work. So upside down A means for all epsilon, which is a positive number. Okay. And I think that is the missing thing here, right? Of the conditions. Yeah. And then this is true. This thing, we can call a sequence convergent if 1, 2, and 3 are true. Yeah, okay, yeah. Usually this thing comes, it applies to this. So they're related conditions. Okay. So, and also in the definition, they have that. Whenever n is greater than, that's what you're saying. So look at the definition. So this thing usually goes before to make it true. That's why number 2, sir. This thing does happen before 3. Okay, or it can be part of that. We'll go over this again as in we take the definition. So let me do this quickly again. So fame is a B if fame is a song, fame can be thought of as having a sting, and fame has a wing. Song means it has a buzz. Okay, fame gets you a buzz, like Taylor Swift with her Swifties. Okay, sting when she voted against Mr. T. So sting means the pitfalls, right? Pitfalls of fame. It has a bite, or maybe fame is sharp. Fame has a wing, and I put in spreads. Okay, all right. Before we go on, I'm going to fix this. So let's fix this thing here. If n is greater than or equal to n, then let's just do implication. If this is true, and then if so these we can put that there, and we start right here. First, there needs to be an n, and then for all the values, all the indices for the terms that are bigger than that, all the terms after this n end up in that interval, and also before everything else, 2. This better also exist for all epsilon. Okay. Let's do, what should we do now? What time is it? Aha. 7 more minutes? Okay. All right. So, is this a poem? So I do have the notes that I'll also email out. Okay. So here are the notes on the poem. So let's go through them, and actually we'll just do it right here. So my question to you would be, number 1, let's think about what the poem, and then the title of the poem is just the first line. Because Emily Dickinson didn't have titles for her poetry, and then later on people just numbered them. I don't know what the number is for this one. She wrote like around 1800 of these things. Can we say that this is a poem? So we're thinking in not at a specific small level. And then on Wednesday, I'm going to go more over how to connect the math with the poetry. Okay. For instance, before I forget, we'll do this on Wednesday. Doesn't this look like a bee? Visually. Which is the body of the bee? That's the wing. Visually, I can see that, right? Then how far does the distance, how far does your fame spread? How big is your epsilon? Is it half? If I become famous, how famous am I? I'm just famous in this classroom. People next door don't even know how famous I am, because my epsilon is barely a classroom length. And then it's because of you guys are here, I'm famous, and I'm only famous with you guys. So my epsilon sucks. Taylor Swifty was having an, what is it? Her little corporate concert. The millions of people right outside. So fame spreads. Okay. So is this a poem of? So visually too, look at it how visually the bee resembles that. There is a wing, and the question of distance, how far, you want to write this down, right? How far does your fame spread? Spreads depends on how good your poetry is. So the poetry, the song could be the epsilon. Fame will spread because it has a wing. If your song or your poems suck, then the fame will not be widespread. Okay, so things like that you can get there. So let's do this. Is this? So now let's go back to a poem of renunciation. Poem of renunciation, renouncing, rejection. Is she rejecting fame? Ish, very good. Let's move on. Is this, and then this is related, is this a poem of contradiction? Very nicely done. Does she fucking want fame or not? No, no, no. So you point, you go, yes, she does. When in the second line, she's excited about it. Third line, she rejects. Fourth line, so in this ish thing is actually right there. Half of it says, I want it. And then the other half says, I don't want it. I'm like I speak at home. It, two, this could be, oh shit, or yes, it has a wing. It will travel. It will make me have readers. People will read my stuff. So you could say that here, what about the first line? This one is this neutral? So this thing is exactly like when we say a convergent sequence. This thing is convergent. This is, so you could say that the first line seems to be a what is this thing called? This is just a term, convergence sequence. We're talking about this sequence has convergence. No. I'm trying to make it sound the same thing. Anyway, let's go back to this. So we're going to say it has song seems to be that fame is desirous. If it's a word, can't seem to spell it. Desirous. What's another? Wants. Is there another word, or we just use desirous? Okay. So it seems like Emily Dickinson desires when she writes the second line. She rejects, renounces. When she writes the third line, in the fourth line, it could be both. So there is ambiguity. All right, let's keep going. Is this a poem? Oh yeah, ambivalence. So this is a poem expressing ambivalence towards the notion of having fame. And then does this poem, is it a poem of consolation, solace? How does she have solace from this poem? By doing the ish. By saying fame is cool, but maybe not for me. And if I don't have it, it's fine. On Wednesday, we'll go more into the